Hello to everyone. I am Dr. Mahalakshmi. Today I am going to discuss about a subject computer organization and architecture. So here unit 1 we are going to discuss. Unit 1 is all about introduction to computer architecture and organization, number systems and logic gates. If you see the introduction for architecture, computer is nothing but an electronic, digital, and general purpose computing machine that automatically follows a step-by-step list of instructions to solve a problem. The step-by-step list of instructions that a computer follows is also called as an algorithm or computer program. Why to study computer organization and architecture? It designs better programs and also including system software such as compilers, operating systems, and device drivers. It will optimize a program behavior and also it evaluates computer system performance. You can able to understand the time, space, and the price trade-offs by studying the organization and architecture of a computer in depth. And also, this computer organization is encompasses all physical aspects of computer systems. Example, circuit design, control signals, and memory types. How does a computer work? We'll discuss about how exactly the computer works. It focuses on the structure of a computer, that is, the components that are integrated within a computer system, and also refers to the logical aspect of system implementation as seen by the programmers. Okay, computer architecture includes many components such as instruction sets, formats, operation codes, data types, the numbers, types of registers, addressing modes, main memory access methods, and various I/O mechanisms. The architecture of the system directly affects the logical execution of programs. So the computer architecture for a given machine is the combination of its hardware components plus its instruction set architecture. It can also be called as ISA. The ISA is the actual interface between all the software that runs on the machine and the hardware. So ISA is a very important component of your computer organization and architecture. It's going to act as an interface between the hardware and the software. Studying computer architecture helps us to answer the questions like, how do I design a computer? In case of the IBM, Sun, and Intel ISAs, it is possible to purchase processors which execute the same instructions from more than one manufacturers. All these processes may have quite different internal organizations, but they all appear identical to a programmer because their instruction sets are actually same. Organization and architecture enables family of computer models, same architecture with a difference in organization and difference in price and performance characteristics. When technology changes, only organization changes, but not architecture. This gives code compatibility. So organization and architectures is an important component and it also has gotten advantages. So if you see the computer components, these are all the important main computer components as we know, CPU, memory, and I/O devices. And CPU is made up of ALUs, registers, and control units. And these three components are connected by three system buses, generally three computer buses. One is data bus, address bus, and control bus. If you see here data bus, they are actually bidirectional. Address bus, it is an unidirectional from CPU to memory or memory to the CPU. And also we have gotten control bus, which are actually bidirectionals. At the most basic level, computer is a device consisting of three pieces as we discussed. A processor. The CPU is nothing but we have gotten processes. This processor actually interpret and executes programs, and we have got a memory, and memory will be of different forms, like RAM, ROM, and also we have got a tertiary memory, cache memory, secondary memory. They'll be used for storing both the data and program instructions. And we have got an input-output device that is also play a very important role in order to in order to feed the input or input and output to the system, and it is actually an interaction between the users and a computer hardwares. So a mechanism for transferring data to and from outside world is being done through input and output devices. Input to communicate between computer and the world, buses are to move information from one computer component to another computer components. So computers with a large main memory capacity can run larger programs with a greater speed than computers having smaller memories. So RAM is an acronym for what? A random access memory. Random access memory means that memory contents can be accessed directly if you know its location. So cache is a type of a temporary memory that can be accessed faster than RAM. Next, if we discuss about the generation of computers, we have got different generations from the inception of the computer technology. First generation, second generation, third generation, fourth generation, fifth generation, respectively, and goes on. And the periods, if you see for first generation, it's from 1940 to 1956. During that time, the circuitry in terms of vacuum tubes we have got, and it has got only the memory capacity of 20 KB and the processing speed of which is 300 instructions per seconds. And the programming language which has been used here is assembly language. An example of computers are UNIVAC, EDVAC. And if you see second generation of computers, its period starts from 1956 to 1963, and circuitry is made up of transistors. Its memory capacity is 120 KB, and processing speed is 300 instructions per second. The programming languages which are used here are high-level languages like Fortran, Gobol, and Allcalls. And examples of such computers are, as given here, IBM 1401, IBM 7094, CDS, CDC 3600, D-Univac 1008. And we have gotten third generation of computers, which period starts from 1964 to 1971. Its circuitry is made up of integrated chips, and its memory capacity is increased from 120 KB to 1 MB. And its processing speeds are 1 micro instructions per second. These micro instructions are in the form of millions. So millions instructions per second speed. It has got the third generation computers, and programming languages also developed with respect to C and C++. And example computers are here are IBM 360 series and 1900 series. And in fourth generation computers, if you see here, it's available from 1971, and its circuitry is made up of microprocessor. So microprocessor era starts from 1971. It is also called as an VLSI technology, very large scale integration technology. And its memory capacity here is semiconductor type and very high memory capacity it has got. Its speed is faster than third generation. And what are the programming languages we have got here are C, C++, Java. Examples of these computers are Pentium series, multimedia, and the stimulations all comes under fourth generation computers. And if you see fifth generation computers, it starts from present and beyond. It goes beyond that, and we still not named, sixth generations. So the circuitry which made up of fifth generation is ULSI technology, ultra large scale integration technology, which is an advancement from VLSI technology. So the advancement for VLSI technology is ultra large scale integration technology. All system on chip technologies will comes under ultra large scale integration technology, which are more faster than VLSI technology itself. So memory capacity is larger than VLSI and VLSI. So it has got a memory capacity of both VLSI and ULSI, and processing speed is very, very, very fast. And languages that are being used are all higher level languages and neural networks. An example of the computers are artificial intelligence computers. Next, we will discuss about the computer level hierarchy. If you see computer level hierarchy, through the principle of abstraction, we can imagine the machine to be built from a hierarchy levels, in which each level has a specific function and exists as a distinct hypothetical machine. So in different levels, the computer itself, we can differentiate into different levels. On different levels, they'll perform different tasks, and their speed of operation will vary. The objective of those operation also would be varying. So abstraction is the ability to focus on important aspect of a situation at a higher level while ignoring underlying complex details. We call the hypothetical computer at each level is a virtual machine. Each level's virtual machine executes its own particular set of instructions, calling upon machines at lower levels to carry out the task when necessary. If you see the level 6 will be the user level. If you see the hierarchy of the computers, it starts from level 0 to level 6. So we have got level 0, level 1, level 2, level 3, level 4, level 5, and level 6. These are the 6 levels we have got in the hierarchy of the computers. Level 0 is a digital logic, with where the digital logic we have got a circuitry in the form of gates and normal circuits with electronics components. And level 1 is nothing but a control unit. In this control unit, the kind of circuitry we have got is microcode and hardwire control signals. Everything will come under level 1. Then in level 2, we have gotten a machine level codes. And these machine level codes are nothing but instruction set architecture. The other name for machine level codes are those software instructions are called as instruction set architectures. And in level 3, we have gotten system software. The system softwares are like operating systems, library codes, all system softwares, all inbuilt libraries will be included in level 3. Then level 4, we have got an assembly language program. All machine level language programs should be converted to assembly level language programs in order to be processed by the computers. So the assembly level language program should be an important thing for interacting with the computers. So which is the level 4. In this level 4, what kind of codes or circuitries we'll be using is assembly codes. And in level 5, we have high level languages which will be used for interacting with the humans, application users. So high-level languages are some of the high-level languages. They are made up of like C++, Java, Fortran, everything will comes under Python, all comes under high-level languages. Then level 6, the topmost layer will be a user, and this user will execute the programs on the computers, and they'll do different applications on the computers. So this user level composed of applications and is the level with which everyone is most familiar. At this level, we run programs such as word processors, graphics packages, or games. The lower levels are nearly invisible for the user levels because they are hardware components. The user cannot able to directly interact or directly can visualize or see the operations which are going under the hardwares. So level 5 is the high level level language, which we have already discussed in the diagram itself. So this is used for interacting when we write programs in languages such as C, Pascal, Lisp, and Java, and Pythons. These languages must be translated into a language the machine can understand. So high level languages will be written by a human being, and it should be converted into a machine level language before it is being processed by the computers by using what? Compilers or interrupters. And then these compiled languages are translated into assembly level languages, and they are assembled into machine codes. Now, they are translated to the next level, next to lower levels. This your user at this level sees very little of the lower levels. As they are high levels, they can't able to see what is happening at the lower levels. So they can see everything with the higher levels. They'll not be able to see, or very less things they can able to see with the lower levels. Next, level 4, if you consider, it is an assembly language level. In assembly language level, it is produced from level 5, as well as instructions programmed directly at this level. We will be programming the instructions at this level 4. And as mentioned, compilers or compiled high-level languages are first translated into assembly level languages, which is then directly translated into a machine level language. This is a one-to-one translation, which is nothing but one assembly level language instruction is translated into exactly one machine level language instructions. By having separate levels, we reduce systematic or semantic gap between a high level language and the actual machine level language. Next bottom up level, if you see from level 4 is system software level. System softwares, these softwares are used for making sure that all the programs are running successfully on the computers or executed by the computers, both by the hardwares and also by the softwares user programs. So some of the system level programs are operating system instructions. They are responsible for multi-programming, protecting memory, synchronizations, and very many other important functions. Without these system softwares, we cannot, the users cannot able to interact with the systems or the hardware, because the hardware is very, very less visible to the higher levels. So only through these system softwares, they can able to interact with the computers. Often these instructions are actually translated from assembly language to machine level language, are passed through the level unmodified. They will not be modified at this level. So if you see here, level 2, it is made up of a machine language, machine levels. So they are consist of what? Instruction set architecture, as we have already discussed in the hierarchy architecture itself. We have seen that in the level 2, we have got instruction set architecture. They are particular to the architecture of the machine. So it will vary architecture to architecture, how the architectures are designed from different vendors. Based on that, they'll be deriving the instruction set for those corresponding architectures. Now, programs written in machine level language need no compilers or interpreters or assemblers. Directly, if anything has been written on machine level language, we don't want any interpreters. If it is written in high level language or assembly language, then we need a compilers, interpreters accordingly, whether we need an assembler or an interpreter. And then level 1 is the control level. A control level unit decodes and executes instructions and moves data through the systems. So control units, if you see, they can be programmed or hardwired. The program can be a micro-programmed or they can be a hardwired. What is meant by micro-program is a program written at a lower level language that is implemented by the hardware. So the programs that are written in a lower level language, low level language, it is known as a microprogram. Hardware control units means they are actually consist of a hardware units. They are directly executing machine instructions. So hardware controllers consist of a hardware units, and a microprogram is consist of a low level language instructions. If you see level 0, this is a digital logical level. This level is where we find digital circuits, and that is the chips, the hardware chips, literally processors, the storage unit, hardware storage unit, you can see in digital logic levels. So this digital circuit consists of gates and wires. These components implement the mathematical logic of all other levels. In this unit, we consist of the following syllabus or the topics. This is introduction to computer organization architecture. So we have got an number systems, different number systems like a binary, decimal, octal, hexadecimal, and also different code conversions we are going to study, like a gray code conversion, BCD, XS3, and ASCII and parity code generations as well. And also we are going to discuss about arithmetic operations like addition, subtraction, multiplication, division, and using sign magnitudes, and also the complements for ones complement, two's complement, and BCD arithmetics. Also, we have gotten logical gates, or logical gates like AND, OR, NOT, NAND, XOR, XNOR. So if you see the definition of a digital system, this is the actual picture of a digital system, how it works, what are the blocks included in the digital system, basic building blocks of your digital system. Basically, a digital system is nothing but it consists of a discrete information processing unit. So in the digital system, we will have a digital signals processing unit, and then this processing unit will be having an input and outputs, and also it has got a system states. So depends upon the system states, that is based on the control signals. The inputs will be processed by the processing unit, and they'll be throwing the outputs at the output end. And because it is a digital system, the inputs will be of a discrete form, and the output also will be of a discrete form. It will not be a continuous form. So it takes digital system, basically it takes a sets of discrete information inputs and discrete internal information and generates a discrete set of information outputs. So what are the different signals which are available? We will discuss about that. So if you take an information, that information can be represented by using a physical quantity. For digital systems, it can be digital units or zeros or ones or discrete values. So if you consider in terms of levels, we can represent signal in terms of two levels or binary values, so zeros and ones, or two levels means we will discuss about it, that is true or false. Those kind of levels we can able to represent, or low or high. By using those levels, we can able to represent your signals. So these are all the different forms of discrete signals. So if you take your binary values, they can be represented by using what? By using a number, a digital number, digits, that is the zeros and ones, or words in terms of symbols. If you want to represent them in terms of levels, or symbols, if you want to represent by true or false, you can able to represent. Similarly, in terms of symbols, again, in terms of digits, if you want to represent, you can represent it by zeros and ones. In terms of word, if you represent, you can be representing it by using true or false. And another level of representing by using symbols is low levels and high levels. Equivalent to zero in terms of symbol, it is false. Equivalent to zero in digits, in symbols, with respect to level, it will be low, and accordingly, for one, it follows consequently. And also the words can be on or off. Like in switches, we have on signal and off signal, right? Those two levels also can be considered as the two discrete signal forms of your digital signals. So these binary values that are represented by values or range of values of physical quantities. So this is how the signal can be represented by using over time. Okay. So with respect to time, if you consider the time unit, so different time units, time unit 1, 2, 3, 4, etc. And how the analog signal will be represented. The analog signal is actually, this is the height is actually voltage. On horizontally, we will be measuring the time periods. So analog signal will be represented like this. That is, they will be continuous in voltage as well as continuous in time period. So if they are varying with respect to x-axis as well as y-axis, that is with respect to time as well as the voltage, then particular signal will be called as an analog signals. If you consider digital signal, there are two different types of digital signals we have got. One is synchronous signal. Also, we have got asynchronous signal. Asynchronous signal is they'll be discrete in terms of the voltages, which is nothing but discrete in terms of the values. They'll be having the values are not continuous. See here, the continuous means it has got, see, from this negative -5 to +5, any value it could be like -5.8, -5.3, or +1.3. Any value it can be represented by using analog signals. But if you take a digital signal, in terms of a voltage, they'll be in terms of a value, it will be represented only with respect to discrete natures. That is, for a low level, there will be one level, one voltage, and for a high level, there will be only one voltage. That is between zero. Suppose if this level is some +5, from 0 to +5 only, it could be represented. In between, values will not be represented by using this digital technology, digital technique, or a digital signal, or a discrete signals. But with respect to time, if you see, they are not constant. They'll be varying with respect to time. So for a certain time unit, it may be very small, and for another time unit, it may be large. They are known as the asynchronous signal. In fact, if you take a synchronous signal, in terms of the voltage or in terms of value, they are same as that of asynchronous signal. So synchronous signal also will be varying with respect to only low level and high level. It has got only two levels with respect to zeros and ones. So it will not be having mediatory values, in between values. So in terms of voltage, they are discrete, and in terms of time also they are discrete. And these are the types of, that is definitions for analog system and digital signal. Analog system means what? The physical quantities or signals may vary continuously over a time. Signal that varies Continuously over time means continuously over time with respect to on x-axis we have a time period and the y-axis will be represented by a voltage. The voltage will be referred here as a x of t. So this voltage is varying with respect to time. So analog signal is nothing but the signal that varies continuously with respect to time. That is known as analog signals. If you consider a digital signals, there the physical quantities are signals. They can assume only a discrete values. They'll be having a great accuracy. So in between, if you see here, the same signal in terms of discrete nature is we have only with respect to these time periods we have got. See at the zeroth time or zero point 0.5 milliseconds or 1 milliseconds alone, we are representing the values. So in between this and this, we don't have the representation in digital signals. So discrete values, okay, discrete values or distinct values alone will be represented by using a digital signal. This is the difference between analog system and digital system. So analog system will be represented continuous with respect to time. They are actually discrete in nature, which are known as digital signals. If you consider binary digital signal, as we have already mentioned that binary values can be represented by using a digits or by using a symbols, and symbols will be taken in the form of a false or true and also low or highs and are also on and off. So if you see the binary digital signals, how they'll be represented is this will be the off and this can be considered as on, and this can take a value of logical one and this will take a logical zero. It will take only two forms. In between, there won't be any forms. So in between values are known as undefined values. So this is the high form. This is the high level, and this is the low level. If you see here, this is the high level, logical one level, and this is considered as logical zero level. In between, the values are known as undefined. This is a representation of a binary digital signals in terms of two discrete values or two physical quantities alone. Thank you all for listening.